Hello to everybody. Two technical communications. Tomorrow, around the break we'll do in the middle of class, we'll have the students' opinion form. I'll lead you to a particular site where it's possible to get this form. I think it's the first time for the ones who were not in the University of Bologna in the previous years. You can find here, course Uniboid, 2 cycle service management students' opinion. Here, this presentation of this thing. I'll talk about that also tomorrow. But please have a look at how the questionnaire is. Okay, there are 2 pages, one with standard answers, meaning completely satisfied, fairly satisfied, fairly unsatisfied, completely unsatisfied over several for several questions. And the second page is with open questions, so where you can, if you want, give us some hints. I must say that they have been very useful in the years for all the courses I've been teaching, and in particular, if I'm going so slow, I have gone so slowly in the first part and solving carefully many exercises is exactly because of the questionnaires of last year, okay? And so please take that seriously, be coherent. For instance, one student last year gave me a very bad score for the interest in my course in the first page. And in the second page, he said, or she said, oh, it's a wonderful course. There are so many things I did not know. So please be coherent. I don't ask you to say only good things, but please be coherent in what you say. Okay? It's not very important for me as I am at the end of my career, but it's extremely important for young teachers because the scores they get in these questionnaires will be also will appear when they apply for a better job, a better role in the university. So, okay. All right, but that will be tomorrow. Instead, next Monday will be almost entirely dedicated to the midterm test, okay? I'll give you all the same test, also to the ones who are here. I've just decided that with, together with the present students. And so you will be treated in exactly the same way if you are here present in Bologna or if you are at home. Okay? The midterm is extremely standard because the questions are exactly the same that you have already in the two examples that you find in the page of the course program. And I'll go through it. Apart from the last 2 questions which will be dealt with tomorrow. And so we'll see together how to answer those questions for example number 1. Okay? This midterm has a maximum score of 24, and the minimum for being allowed to the oral part is 14 over 24. Okay, and principally it is dedicated to this, to the admission to the oral part. So if you fail or if you want to improve your score in the midterm, you will have opportunities later on. But please be all present next Monday for this midterm. And take care of having paper and pen for solving things, and a smartphone or whatever, a scanner or whatever for sending me what you have written, what you have answered. Okay, you don't need to use to print what I'm giving you and answer on that printed sheet. You can write the answers, numbering them according to the numbers that you find in the printed sheet, and answer on your own paper, and then you take a picture or scan it and send it to me, and you'll see how through EOL. Okay. Echo Oscar Lima, if I'm not wrong in the NATO alphabet. Okay. All right. So I think we have seen whatever was used here. And let's see. This is example one, and so it will be exactly like this with, of course, a different graph here and other graphs in the folder. Okay, so you're given a graph, and the first thing you are asked for is its adjacency matrix and incidence matrix. Oh, sorry, I see that I have probably a question. Midterm next Monday, yes, at the class time. And thank you, Ali, for answering.
Professor, hi.
Hi.
Excuse me, can you start the record, please? I don't know if it's recording.
Sorry?
I don't know if it's recording the session.
I don't know. I think I've not. Thank you very, very much. Good. No, it is recording. Thank you anyway. If you have doubts, any kind of doubts, please tell me. Okay? Thank you. All right. Oh, no. Here and here. Okay, so adjacency matrix, incidence matrix, it takes some time to write them down, but let's see the answer. Adjacency matrix is like this, and so you have on the rows and on the columns the vertices that you have, which will always be in capital Latin letters, and so let's see, for instance, this row. From A to A, do we have any edges? No, none. From between A and B, yes, one. A and C, none. A and D, none. A and D, yes, we have one. A and F, yes, we have one. Since it is undirected, the matrix will be symmetric. So the same thing that we have on this row will be in this column, and so on and so forth. So from B to A, we have already seen that, okay? From B to itself, nothing. From B to C, 1. From B to D, 1. From B to E, 1. And from B to F, none. So this is the row for vertex B, and so on. Incidence matrix, on the contrary, has rows indexed by the vertices and columns indexed by the edges, will be in small Latin letters, okay? And so for each edge, you have to see to put a 1 for each vertex, which is an end of that edge. So edge A, you have 1 and 1 in the correspondence of vertices capital A and capital B, and of course zeros for all the others. What about, let's say, edge G? Edge G has ends which are B and E, and so we'll have 0 in correspondence of A, 1 in correspondence of B, 0 for C, 0 for D, 1 for capital E, and 0 for capital F, okay? And write it down, okay? Then, minimum degree small delta, maximum degree capital delta, okay? And I don't understand how so many students in the past passed the midterm, but at the oral did not know what a small delta is. They wrote small delta in a formula, and that's what is small delta. They were not able to tell. Okay, small delta is the minimum degree. So here it's easy because it's a small graph. They are all small graphs, the ones I give. And so here we have 2, 3, 4, 2, 3, 4 as degrees. And so the least possible degree in the graph is 2. And what's so small delta is 2. What's the maximum degree capital delta? We have just 2, 3, and 4, and so 4 is the maximum degree, okay? So you have 2 for small delta and 4 for maximum degree capital delta. Now, connectivity and edge connectivity. This is something for which you scarcely use the theorems. We have just the definition, after all. The only theorem that you might keep in mind when solving this little part is that kappa, the connectivity, is less than or equal to kappa prime, edge connectivity, which is less than or equal to small delta, okay? And actually here, what do we have? We can start by looking at a vertex with the least possible degree, this F. And actually, if we delete edges E and F, of course, we are increasing the number of components. It is a connected graph, so from one component we get to 2 components, one given by A, B, C, D, E, and the other by F alone, okay? And so it's what the theorem just tells us, that the edge connectivity will be at most 2. But is it possible to have 1? Well, this is fairly easy. If the edge connectivity were 1, we would have a cut edge, an edge, since this is connected, an edge whose deletion would make the graph disconnected. No, we don't have any cut edge here. It's very easy to see. Okay, so actually, kappa prime is 2. Do we have, and so necessarily, the kappa, the connectivity or vertex connectivity is either 1 or 2, okay? Not more because of the theorem. And if it were 1, we would have a cut vertex. Do we have a cut vertex, a vertex whose deletion makes the graph disconnected? No, but we see that we can, for instance, delete E and A, the other ends of these 2 edges, okay? Or E and B, okay, and so on, or D and B, and we have the possibility of disconnecting the graph by deleting 2 vertices. So, again, connectivity kappa equals 2, edge connectivity kappa prime equals 2 as well, okay? Then, is G bipartite? Why? Okay, why is in the sense that I invite you to use the characterization theorem for bipartite graphs. The definition of bipartition is it is possible to divide this set of vertices into 2 parts so that all edges have one end in one part and the other end in the other part. Call these 2 sets X and Y. All edges should have one end in X and one end in Y. Okay, and so one could try to subdivide these 6 vertices in all possible ways. No, we have a theorem which tells us the graph is bipartite if and only if all its cycles are even. It means are made of an even number of vertices and even number of edges. But here we find just one is enough, but we find several odd cycles, so we are sure that the graph is not bipartite. In the case it is bipartite, and you see that because you find that no odd cycle is there, you are also invited to list the two vertex sets of the bipartition. Okay, it's not the case here because this is not bipartite, but if it is bipartite, please give the two sets of vertices of the bipartition. Okay, then we have Euler, the question about being Eulerian. Two questions about that. Does G have an Euler tour? So starting from one vertex and going through each edge exactly once and coming back to the original vertex? No, and we discovered that not by trying again, but because of a theorem. It tells us that such a tour exists if and only if all vertices have even degree. But we have these two vertices with odd degree, and so there does not exist an Euler tour. Does there exist an Euler trail, not claiming that you arrive back to the original vertex, but still that you go through each edge exactly once? Yes, and again we have the theorem telling us whether it's possible, and it is possible if and only if you have exactly two vertices of odd degree. And we have exactly two A and D of odd degree, so it is possible, and you are also invited to give such a trail, okay, which will then start on one and then on the other, okay? You can do it just by looking. It is so small that you can do it without any use of algorithms, or if you want, you can use Fleury's algorithm as we did as in an exercise last time or last but one, okay? And so in this case, I tell you such a trail A, B, C, D, E, A, B, C, D, E, A, B, C, D, E. Oh, well, this is easy. I go around A, B, C, D, E, F, I, G, H. But you can do also in another way. A, E, B, you have different ways of solving. This is not the only one, but you have to give me one such trail, okay? Does G have a Hamilton path? In this question, I could instead ask, does G have a Hamilton cycle, okay? But if it is a path, it does not end at the same vertex of the start, okay? In this case, again, no use of theorems, just look and it's possible to touch all vertices exactly once, and since it's a path and not a cycle, not coming back to the original vertex. So A, B, C, D, E, F is the easiest one, but you can also have more fantasy than me and find other Hamilton paths, okay? Then maximum matchings, okay? And here I give one particular maximum matching, C, G, F, C, G, F, these three vertical edges, but there are some others which are, for instance, you can use A, E, and C, or B, D, and F. Okay, there are quite a lot, no, not quite a lot, but not just one. There are several maximum matchings, all of three, and each of these is actually a perfect matching, meaning that every vertex is saturated by that matching. Of course, you must know what the perfect matching is, okay? Then we have weights on the graph, okay? Like this. And we have to use both algorithms that we have learned. First, dice from A, and then Kruskal's for an optimal one, okay? And what do you do with the dice? You start in A, which has distance 0 from itself, of course. Start with choosing the edge with an end in A with least possible weight, and it will be this F with weight 7. Okay, so F is at distance 7. Okay, and next 7 plus 6 is more than 9 and 8. So next we'll take A, which has 8 as a weight. So B will be at distance 8, okay? And then 8 plus 5, 8 plus 3, 8 plus 4, and 7 plus 6 are all bigger than 9. So next will be the use of edge 9, and so we'll land in E, which is at distance 9, and then on like this. And so since we write down these distances, it's easy then to see what to put next. Okay, 7, 9, 8. So if I do 8 plus 4 and 8 plus 3, it's always more than this 9 plus 1. So the next one is D, which gives us distance 10 of D from A. And finally, which edge do we have to choose? Well, from B to C, 8 is the distance of B, and 8 plus 3 is 11, and so we take this, okay? And this is the spanning tree of the least possible, the minimal routes from A to all other vertices, okay? And I know that probably many of you have done something like that with another way of indicating things. It's all right, no problem, okay? The important thing, do not confuse Dijkstra's with Kruskal's problem and algorithms. Same graph, but now we are asking for a spanning tree with minimum total weight, which will not be the one we have here in general. I'll take care not to do it equal, okay? Sometimes it is the same one. In all these cases, and with high probability in the one I'll give you, I've not yet prepared it, they will give different results. So what do we have to do for Kruskal's algorithm? Pick up an edge with minimum weight. So surely pick up D, which is with weight 1. Okay, then pick up another of minimal weight of the remaining ones, but making sure that it does not close a cycle. So we have this C with weight 2. Okay, does not close a cycle. Next, we can pick up this 3, okay, which does not close a cycle. But we will not be allowed to take G, because even if 5 is the least remaining weight, it would close a cycle, and so on and so forth. And so we don't take 5 because of this. Next smallest weight is the 6 of edge E. We can add it because we do not close a cycle. And finally, do we choose 7, 9, or 8? We choose 7 because also it does not close the cycle. And what we get here is an optimal connector. You can go through red edges from each vertex to each other vertex, and the sum of weights will be the least possible for such a total connector, okay? The last one we can answer today is this question 12, which is use the recursive formula for computing the number of spanning trees of this smaller graph, okay? And so now I'll do it, okay? Yes, I should. Okay, no, I will not copy the names. Okay, so I start from here. We have okay, and then oh, it's very ugly. No, it's too ugly. This is nicer. Okay, so what do? We split things. Do it small. We split things like this by taking this edge on one side, we delete it, on the other side, we contract it. Okay? And so we have that. I delete it here. I contract it here. Okay? And now, here I now pick up this one, and on one side I delete it. On the other side, I contract it. Which gives me two multiple edges, okay? Here, we can use the same, but it's not important to use the same we use on the other side. We, again, split into two. On one side, I delete the edge. On the other side, I contract the edge. And here, above, I do not want to do any more things because I gave you some tricks and I'll use them. And we could do the same thing here. Okay, I'll do the same thing here, okay? And I'll divide only this, and then let's see what we can say. Okay, I pick up this, and so on one side, I delete it. And on the other side, I contract it. Okay, so now let's count. Let's count what we have, okay? So here we have 1 because it is a tree by itself, okay? So the number of spanning trees of a tree is 1. Here what do we have? We have a cut vertex, this cut vertex, okay? And do you remember what we have? That we have the product of the toe of one side times the toe of the other side. And so this, we could say that it is this times this, okay? And so, what do we have? This is 2 times 1, okay? And so it is 2. Here, we have this. okay, which is a cut vertex. And so we can say that this is this times what? Times a cycle, okay? And we know what we have when we have, well, this is a tree by itself. This is a cycle of 3. And so when we have a cycle, it is 3. So here we have 3. And again, here we are in more or less the same situation as before. And so we have this times this, okay? Which means 2. And here we have 3 because we have 3 multiple edges, okay? So 1 plus 2 is 3, plus 3 is 6, plus 2 is 8, plus 3 is 11, which is our final result, okay? And remember that in the oral, it is fairly easy that I ask you for one of these. What is this 11? It's the number of spanning trees that you have here. Can you show me 2 spanning trees of this graph? Okay, I put one in red, for instance. It could be this, and I can put one in green, which could be, for instance, this, and this. Okay? Just to, can you give me 2 of these 11 spanning trees? Here it is. Okay? You cannot? I'm sorry. Come next time. All right? All right. The next two questions will be, oh, sorry, where it is? Where is it? Next ones are for tomorrow, okay? Any questions about this?
So, sorry, the bipartite, the graph is only bipartite, it has an even cycle, which means even edges and even...
Well, in a cycle, the number of edges and of vertices is the same. This number must be even for all possible cycles. This is a theorem we have seen, okay? And if you say, well, if you say it is bipartite, you don't have to write anything more than the bipartition. If you show me the bipartition, I don't need any other reason for saying, okay, you exhibit that it is bipartite. But if you say no, if you don't use the theorem, you should list all very many possible bipartitions and show that none of them adapts to the condition for bipartition. Okay, so you use the theorem. You spot at least one cycle, one odd cycle, and that's enough for saying, no, it cannot be bipartite because of the existence of the presence of that odd cycle. It has odd cycles is enough for saying it's not bipartite. Okay? As well as it has a vertex of odd degrees enough for saying it has no Euler tours. It has 4 vertices of odd degrees. It's enough for saying it does not have even a trail, an Euler trail, because 4 is more than 2, and so on. Okay, using theorem in those cases, and be careful. I've seen not many, but some midterm tests answered in such a way that somebody, okay, I take out 1 point, but I should take out 5 points if somebody tells me that the connectivity is greater than the edge connectivity, which is greater than small delta. You must know theorems, and so if you are convinced that this number, and this number are not in the correct situation, you should see that you are going against a theorem. And so theorems are better than what you think, because they are very, very certain. And actually, there is a proof that you can check. Okay? So be careful not to write something which goes against the theorems, or even worse, the definition. Any other questions about this? Okay, so now we can go on with our theory. We had just started edge colorings. I must tell you, after edge colorings, we have a very nice chapter which is independent sets and cliques, and then we'll have vertex colorings. But edge and vertex colorings, apart from the name, are connected together by one thing. Vertex colorings was the first to be studied, and it was, again, because of something futile, in the sense that it was a question raised by a student which was not easily answerable and was a big question not in the pubs, maybe also in the pubs, surely in the university pubs in England. And then the question came from the second half of the 19th century, and it was very simple. The question is this: take a political map, so regions, okay, and consider adjacent two regions if they have at least one piece, not just one point, but a piece of common boundary, okay, an arc, a segment of common boundary. A point is not enough, okay? And the question is, how many colors do you need for coloring a political map, not just one existing, but one you could invent, okay, so that adjacent regions have different colors? Okay. That guy, student Guthrie, was the one who posed asked the question, was using only 4 colors for whatever map he was using, finding, or inventing. And so this was the question. Well, it's easy, try one, to build a map for which 3 colors are not enough. Try to invent one, it's very simple, okay? And it was easy to prove, it was rather early proved, that 5 colors are surely sufficient for any map, okay? And the problem was 5 or 4, and so there were the ones looking for a counterexample needing 5, and others who wanted to prove that 4 were enough, okay? And the thing went on for a long time, in the sense that it became a very serious problem. Why? Not for an immediate application, even if at the end of this chapter and of chapter 8 we'll see applications, okay, of these techniques. But the interesting thing was exactly the question is so easy and you can't find, and you try, and somebody thought he had found a proof, okay, and everybody say, oh, good, how good you are, and he died very, very happy, if one can die happily, and he did not know that his proof was bugged, that it had a very serious bug, which was found a few years after his death, okay, and so the problem was open again, and very much was tried in order to solve the problem. One is chapters 8, vertex coloring, meaning you do this. You transform the problem on a map into a problem on a graph, putting a vertex in each capital town, so to say, and putting an edge between 2 capital towns if the 2 states have common boundary are adjacent, okay? And so now you are not talking anymore about regions, but you are talking about coloring the vertices of a graph. And that's why we have the chapter vertex colorings, okay? Some of the very many attempts to solve the problem instead went to edge colorings. And so this chapter is a child of that big problem, okay? I'll tell you tomorrow about what happened to the problem. It's interesting also because, you'll see tomorrow. But just to say, how come are we interested in edge colorings? The original reason was because through edge colorings there was an attempt, a failed attempt, to solve the four-color problem I mentioned, okay? But still we have something which is there, which could be existing by itself, which has relations, an evident relation with the matchings, and a more hidden relation with Euler tools. I don't give you the this lemma, and of course it's proof, but in the proof of these things you see that we might need to use Euler tools. So this part of the theory is tied with the other parts of the theory, and this is always interesting. Let me go very quickly through these lines which I read at the end of last the last lecture. How online students will send the exam once that it is scanned in PDF? Okay, it will be in EOL. Go to eol.unibo.it if you want to see how it is organized. There you'll find at the correct time the text similar to the one we have just seen, and there it will be possible to upload what you use. Ali, thank you again for answering Farokh. The chapter of the last two questions is chapter 8, which we'll see in detail tomorrow, okay? So, of course, no more than that, since after that we have the midterm, okay? Okay, sorry if I answer so late, just when I realized that you have something on the chat. Okay, so quickly, KH coloring of a loopless graph, no loops from now on here in this chapter. An assignment of K colors to the edges of G. The coloring is proper, and this will be our main goal, to think of proper coloring. If no two adjacent edges have the same color. Adjacent meaning as always having a common end. Alternatively, a KH coloring can be thought of as a partition of this edge set, where here an index I is missing, where EI should be, denotes the possibly empty subset of E assigned color I. Okay, put an I here, please. A proper KH coloring is then a KH coloring E1, E2, EK, in which each subset EI is a matching. Do you remember what a matching is? A set of edges such that no two edges of this set have a common end. Okay, and so if the coloring is proper, if you pick up the set of edges of one of these colors, of course it is a matching. Okay, in the sense we have seen. Okay, so here is a connection to the chapter matching. And you can see in 6.1, figure 6.1, a proper four edge coloring, in which color 1 is for A and G, A and G. These are the names, okay? Of course, you can use all the, as many colors as we have edges, but we want to use as few as possible. So you can have E and G for color 1, B and D for color 2, B and D for color 2, C and F for color 3, C and F for color 3, and D by itself for color 4. Okay, it's not the only proper coloring with 4 colors. Okay, there are also other colorings. It's not a matter of how many colorings there are. It will be a problem in chapter 8, but now we don't mind how many proper colorings we have. We just want to know how little can the number of colors be. Okay, and this smallest number of colors is this phi prime. Phi is this Greek letter. Phi prime of G is the minimum possible color for which there exists minimum K, for which there exists a K edge coloring of the graph. It can really verify that the graph of figure 6.1 has no proper 3-edge coloring, okay? And so it is 4-edge chromatic, since we find a 4 coloring. Let me do it here. Okay, let's use this. And so if we put color 1 here, color 2 here, color 3 here, of course we need at least 3 colors, because we have vertices with degree 3. And so these 3 must be of different colors. And so that this phi prime is greater than or equal to capital delta is immediate, okay? Can it be greater? Here we have an example in which we need more than capital delta. In fact, 1, 2, 3, you can permute them, it's no problem, okay? Now, what can we do? We can repeat 3 here, for instance, okay? And we can repeat 1 here. We don't need a new one, okay? And here, this is maybe not a very nice idea. I prefer to put here a 2. Okay, and so I can use a 1 here, for instance. But then anyway, I need a 4th color here. I think that if I did like I did before, then I would be forced to add a 5th one. But okay, let's try. 1, 2, 3, 3 here, 1 here, and here could I use 1 Could I use 1 here? No, because of this. Could I use 2? No, because of this. Could I use 3? No, because of this. And so I need a 4. But then, could I here use... well, no, it would... No, I could not use 1 because of this. I could not use 3 because of this, not 2 because of this, and not 4 because of this. I would need to put a 5th. So here 4, and here I would even need a 5th one. But then I would be a silly person, because with the smarter one, the red one, I would only need 4. But you try if you want, but you cannot find a coloring of the edges with only 3 colors. Okay, 4 are necessary. Of course, if you have 4, you can use 5. If you start well, you can use the minimum possible. But you see, I started badly, putting 1 here, and then I even need to use 5. But it is not a 5. It is 5 colorable, of course, but it is even 4 colorable. So he prime of this graph is 4. Okay, of course, we have that he prime is greater than or equal to capital delta, because capital delta means the maximum degree. So there is a vertex where we have capital delta edges coming together to the same vertex, and they have to be colored in different ways. So he prime necessarily is greater than or equal to capital delta. How far are we from capital delta? We'll see that. We can have a strict inequality, because we have just seen that in that graph, capital delta is 3, but we need 4 colors. And we now will see, no proof, that tight graphs, we have just capital delta. Nothing. I just want you to have a glimpse here. And here it is. If G is bipartite, then he prime equals capital delta. Okay, and actually that graph is not bipartite. Vizing's theorem tells you that you cannot go much further than capital delta. If G is simple, of course, if you have multiple edges, then you can do horrible things. But if G is simple, either he prime equals delta or delta, capital delta plus 1. So no big possibility, not many possibilities for edge coloring. Okay? Nothing more to say here, apart from a small application. Timetabling problem, of course, here it's written for a school, but you can imagine many industrial situations which are similar to this. In a school, there are M teachers, x1, x2, xm, and then classes y1, y2, yn. So we are in a situation of bipartite graph coming very naturally. Given that teacher xi is required to teach class yj for pij periods, okay, schedule a complete timetable in the minimum possible number of periods, okay? And so how can you do that? It's known as the timetabling problem, and we can use edge colorings for that. Okay, the edge colorings, we have just seen 2 small statements of theorems, but there are algorithms also. But we don't see the algorithms anyway. Just remember that there is a whole theory about that and not just these 2 theorems. So we represent the requirement by bipartite graph with a set of vertices representing teachers, a set of vertices representing class, and then it's not a simple graph. You join each teacher to each class with as many edges in parallel as there are periods that that teacher must teach that particular class. Okay? So at each class, of course, at each period, you must have different teachers teaching different classes, okay? Apart from gymnastic or something where you could have several classes for one teacher, okay? One teacher must have in that moment, in that particular hour, just one class, and one class must have one teacher. So what you have is that at each period you have a matching, okay? meaning that you have matching in the literal sense of the term, matching one teacher with one class in that particular period. How many periods do you need? Well, as many colors you need for coloring, proper coloring that graph, okay? And so you get that number, and if you use the algorithms for finding edge colorings, best edge colorings, then you get how to use the minimum possible number of periods for having all teachers teach all their hours to all classes. Okay? 10 minutes break, and then we go to a chapter I like so much. In particular for the Ramsey part, we'll see, which is rather difficult. So 1806, 1816, we'll start again.